Yeah, so our theme is adaptive network model for aggregation and Prion-like spreading propagation of alpha-synuclein in Parkinson's disease. So Parkinson's disease is synucleinopathy, and it is characterized by cardinal motor symptoms, which is the pattern of Parkinsonism, which is bradykinesia, rigidity, and resting tremor, and some other inclusion criteria. And it is characterized by a loss of dopaminergic neurons in substantia nigra because of the aggregation of alpha-synuclein, which exists normally in normal states in the brain, but starts to aggregate because of some toxic processes that are going on. And that leads to formation of Lewy bodies, and they disrupt neural signaling and loss of mitochondria normal functioning and so on. So one of the main ideas which can lead to toxicity of alpha-synuclein is disrupted lipid homeostasis. For example, here on the first picture, you can see how alpha-synuclein affects lipids and how lipids can affect alpha-synuclein. So it goes both ways. And the idea is disrupted lipid homeostasis leads to disrupted alpha-synuclein homeostasis and the other way around. And alpha-synuclein starts to bind to disrupted lipids or really curved lipid membranes, and they bind to vesicles and to membranes, and they disrupt vesicle trafficking and so on. And like, for example, you can see here how alpha-synuclein and lipid homeostasis is disrupted. And one of the most common explanations of how Parkinson's disease can be caused is because of genetic and environmental factors. And one of the most greatly investigated genetic factors are gene mutation in SNCA gene, which is responsible for alpha-synuclein itself, and also some mutations in genes that are responsible for other proteins, for example, SMPD1 gene, which is responsible for enzymes. Yes, and after we have aggregation of alpha-synuclein, it leads to further propagation of alpha-synuclein in brain, so spreading from alpha-synuclein from one cell to another. And there are four main, postulated ways of propagation of alpha-synuclein in brain. So the first one we can mention is through synapses or synapse-like structures, which is really common because there's our neurons, they have synapses. So one cell signaling to another, what leads to the propagation of alpha-synuclein in these synaptic vesicles. Also through nanotubes, you can see it's here. So this is basically the bond between one cell and another. So it can be a connection between neurons and glial cells, so supportive cells of neurons in our brain. Also different ways of endocytosis, you can see so vesicles going from one cell to another, and different variations, for example, clathrin independent, and also receptor mediated uptake. You can see it over here. So the protein binds to receptor, leads to the further uptake to the cell, and of course the further aggregation and propagation for the cells too. Yes, we can see the vesicle, yes, of our alpha-synuclein vesicle and the mediator in vesicles released with alpha-synuclein. And so this is our conceptual model. So we start from mutations, possible mutations, alterations in gene responsible for enzymes and for alpha-synuclein, and risk factors, which can also be some gene alterations, which we don't really investigate it much, so we don't really know much about them. However, we have to include them in our model because we don't really know, again, what really causes Parkinson's. And here also some other risk factors, which can be metabolic syndrome, different patterns of metabolic syndrome, or for example, dairy consumption, emissions, infections, but also on the other hand, protective factors like smoking, caffeine consumption, ibuprofen consumption, and so on. So this whole pattern leads to disrupted lipid homeostasis and alpha-synuclein disrupted homeostasis, which therefore will lead to alpha-synuclein toxicity, which can be, again, influenced by some protective factors. And alpha-synuclein toxicity leads to aggregation, which can influence seed formation, as well as alpha-synuclein toxicity itself, which therefore goes to four mentioned earlier propagation ways, which stands for alpha-synuclein spreading in brain, like level, and which consequently leads to neurodegeneration. Yes, so moving on to the 3D model of our conceptual model. So on the base level, you can see here our conceptual model laid on it. So, and on the first adaptive level, you can see 4 V states. The first two, so for adaptive connection, they stand for lipid homeostasis disorder, what influence alpha-synuclein toxicity, and alpha-synuclein homeostasis itself, what leads to alpha-synuclein toxicity. They both influence on alpha-synuclein toxicity, but in different ways. I mean, we don't know one more time how exactly, but we know they do it in different ways. That's why we're choosing 2 different adaptive connections for each of these. And the more toxicity we have, the more like common knowledge as a state it will have, and the more impact on alpha-synuclein toxicity it will have. Moving to the third, we state this is for synuclein, aggregation of alpha-synuclein and seed formation. So the more aggregation we have and the more seed formation, it would lead to the more seed formation itself, and aggregation will influence the speed of it. That's why this must be an that's why we chosen this one for adaptive connection. And the last one here for this state is alpha-synuclein spreading overall, and what leads to neurodegeneration. One more time to show how the speed of this one influence the neurodegeneration. We show this one as adaptive connection. And so now we will look at 2 cases. The first case is when we have definitely mutation in alpha-synuclein genes and enzyme genes. Some of them would definitely lead to neurodegeneration. We have protection factors, but they are not sufficient, or they do not play a significant role in protection from neurodegeneration. So you can see the simulation over here. So we used allogistic function for every state except for protection factors and risk function over here, which is here repetitive blue and purple line over here. So when we have mutation, they're lying here on the level 1 because they exist and they're not going anywhere. Every state is going significantly up and very steep because these mutations are definitely lead to neurodegeneration. You can see 4 levels, 4 lines over here, which stands for different levels of propagation because they are thought to not influence the overall level of propagation in the same way. So the least one, for example, is thought to be just simple endocytosis, simple exocytosis. The most popular one is thought to be the receptor-mediated uptake, what was shown also by studies. But what's important here, when you see that protection factors are falling, you can see a slight increase over here in lipid homeostasis and alpha-synuclein homeostasis disorder. But when the risk factors are falling, you see the slight decrease in alpha-synuclein homeostasis and lipid homeostasis. But if you compare these two, you can see that in absolute value, the risk factors are more risky than protection factors are protective over here. And of course, it might influence the homeostasis, but if you have the neurodegeneration already, it won't go anywhere and there is no turning back. But it might slightly influence homeostasis, but it's not enough to influence the general image.
Yeah, and we have the second case when there are some alterations in genes and there are some risk factors, but the protective factors play a huge role. Again, we don't really know what role they play. However, we know that we see patients that do not develop neurodegeneration in early onset, and they develop it really late. It's only about like 1% of people that develop Parkinson's are like over 65-year-old. So here we see neurodegeneration line, which is going up like really comparatively slowly, and as well as lipid homeostasis, alpha-synuclein homeostasis, alpha-synuclein toxicity, and we see here like the line which corresponds to 1, which is like protective factors that influence all this pattern. And we see risk factors that again follow the step mode function pattern, but they do not influence the pattern really drastically. So they influence it as well as mutations, some alterations, which are already also risk factors. So neurodegeneration is developing slowly, and it is developing on a late onset rather than early onset.
Yes, so moving on to conclusion, we provided the model that unifies the processes of possible aggregation and possible propagation ways of alpha-synuclein in brain in Parkinson's disease. And so the main focus of the model was to study alpha-synuclein and lipid homeostasis alteration, so how they interact with each other, because lipids are one more time are thought to be the very crucial factor in alpha-synuclein disorder and other synucleinopathies as well. And so we studied and received the patterns that present different ways of how risk and protective factors can play a role in neurodegeneration, although we don't know what exact mechanism of these factors are. So this may be a field for future studies. For example, the case 2 was based on caffeine consumption. It was proved by one study that if people with neurodegeneration genes drink much, like really much coffee, they had a late onset. How much of a delay we might have, it's unknown, because the usual onset of Parkinson's disease is like 60 years. In Netherlands, if I'm correct, it's 63, the average age of people with Parkinson's. So you see that the person is already old, and how much of a late delay, it might be like 70 years. But when people die, we might not really tell one thing for another. Was it because of the late onset, or was it because the person was already old and it was dying? So the influence of different risk and protection factors is a field for future studies. Thank you for attention.